The Aerospace Academy is a co-production of the Fairfax Network and the Smithsonian National Air and Space Museum Stephen F. Udvar-Hazy Center.
Welcome to the Aerospace Academy. Today you're enrolled in the Design a Satellite Lab. Your mission is to design the next generation satellite for NASA. Before you start picking out solar panels and antennas, you'll need to learn a thing or two about space science. And you're in luck. Our classroom is one of the coolest classrooms you'll ever be in. It's the Smithsonian's National Air and Space Museum Stephen F. Udvar-Hazy Center. The museum hosts school field trips for students ready to learn. And in the space hangar, thousands of amazing artifacts are on display for you to learn from. Today, your teachers are Aaron Whistler and Dick Unser. In today's lab, we'll be using an activity sheet. And you can find that same sheet online. Click on the lesson plan to find a ton of resources. Now, get ready to become a satellite engineer. Pay close attention throughout the show to the satellite elements that are needed for your design. Let's get started. Welcome to the Academy.
Well, welcome to our classroom full of fourth grade students from Sunrise Valley Elementary School here in Reston, Virginia. And we look forward to participating in this classroom with us. And we're going to learn about satellites today. We're going to learn about where they are in space, what they're made of, what they do for us, and all sorts of things. But first, to get started, I want to ask our students here, well, have you guys ever seen a satellite? And what is a satellite? You know, what do we talk about when we talk about satellites? What do we think here? Brian, what?
I've seen a satellite on an IMAX movie. It was the Hubble satellite. It like takes pictures of
Hubble satellite. Yeah, Hubble satellite. That's a good man-made satellite, something that we make. Well, how about over this table? What do we have here? Jess, what type of satellite have you seen?
I've seen a GPS satellite.
A GPS satellite, a satellite used for navigation. Well, you know, you've both mentioned man-made satellites, but actually there's also other types of satellites we call natural satellites, satellites that are celestial bodies. And let's see about that. I think actually, you know, we may live on a satellite. What satellite do you think we might live on, Isabel?
Earth.
Earth, yeah, okay, we live on Earth, and we would say that Earth is a satellite because Earth goes in a path around another big object. What's that big object? Aaron, what do you think?
The sun.
The sun. Aaron, let's see what that looks like.
Sure, sun. Can we come have you out here? Okay, the sun is the star at the center of our solar system, and it's huge. It's 99.8% of the solar system's mass. And as the class pointed out, the Earth orbits around the sun. So Earth, would you take a walk for us around the sun? It takes the Earth about 365 days to get around, and you're doing a great job there. Nice path, Earth.
And let's see, I bet you when you look up at night, you see a natural satellite in the sky. What do you think it is,
Let
Max?
her go around you once or
The
twice
moon.
before you walk.
The moon. All right, hey, Aaron, can we add the moon to this?
Sure, we have them right here. So let's see the moon go around. So the moon's the Earth's only natural satellite, like they talked about. And as you can see, our Earth is still orbiting the sun. Earth, give the sun a little bit of room. Okay, we don't want to have a collision. So you can see there's a lot going on in our solar system all at one time.
Oh, great job, Moon. These natural satellites inspired scientists and engineers to build and launch artificial satellites. Let's take a short break from the classroom to look at some early models. Doug, the Chief of Education at the Udvar-Hazy Center, is on standby to show us more.
Hanging just above the space science exhibit, you can see that these early satellites all had different shapes and features. In the late 1950s, scientists were challenged with the question of how best to design a satellite to successfully reach orbit and transmit information back to Earth. On October 4th, 1957, the Soviet Union was the first to succeed with the launch of Sputnik.
Today, a new moon is in the sky, a 23-inch metal sphere placed in orbit by a Russian rocket. Here an artist's conception of how the feat was accomplished. A three-stage rocket. Number one, the booster in the class of an intercontinental missile. 500 miles up, the artificial moon is boosted to a speed counterbalancing the pull of gravity and released.
Sputnik's radio signal became a symbol of the Cold War space race. American scientists and politicians were anxious for supremacy in space exploration.
I consider our country's satellite program to be well designed to achieve the scientific purposes for which it was initiated. We are, therefore, carrying the program forward in keeping with our arrangements with the international scientific community.
Just 4 months later, Explorer 1, a 6-foot, 30-pound bullet crammed with scientific gear, became the first successful satellite launched by the United States.
The moment is at hand. The countdown reaches 0. Some 3 minutes later, Explorer is in orbit, broadcasting to the world its coded scientific data. Cosmic ray intensity, meteor impact, solar radiation. These are the dry facts that will help carry man ever farther into the age of space.
In July 1958, Congress passed the Space Act, which created NASA. The Explorer program launched over 90 space missions. Explorer 6, nicknamed the Paddle Wheel satellite, was the first to produce images of the Earth using a camera. By conducting experiments in space, these early satellites changed the way scientists learn about the Earth. Now it's your turn. It's time for you to take flight and see the Earth from the perspective of a satellite. Get ready to soar above the atmosphere.
Let's start above the U.S. Capitol building in Washington, D.C. I see on the right, they're working on the new visitor center. Cool. A hot air balloon. Whoa, watch out for that helicopter. Now to the edge of the atmosphere. Things look a lot different up here. That's a Lockheed U-2. And for the big picture, it's into space. Hey, that's a GOES weather satellite. Ugh. Talk about a runaway elevator. And we're back where we started. As you can see, the higher we go, the more our perspective changes, and the more we can learn.
So if the perspective of a satellite in space helps scientists learn about the Earth, how far into space does a satellite need to go, Dick?
That's a really great question, Matt. Basically, where the satellites are and how far they are from the Earth depends upon its mission and depends on what satellite's going to be used for. So let's think about what types of things, what types of missions do satellites have? Can someone think of one that what they use satellites for? Brian, what do you think?
They use satellites to take pictures of farther into space than we can go into, like other solar systems.
Okay, so sometimes they look out into space. All right. How about Gotti? What do you think?
The weather.
Okay, so we observe the weather from satellites also. So sometimes, again, we look at the weather, we use them for navigation, we use them for lots of different things. And basically, to do this, they have to go in specific orbits. And these distances from Earth that they're at, what we want to think about is there's a whole bunch of orbits. There's a whole bunch of orbits that satellites can be in, but we're just going to look at about 3 types of orbits today. So let's let Aaron take a look at where these orbits are.
All right, thanks, Dick. All right, so Earth, I'm going to have you come join me, and Moon, I need you to go way out into space. All right, that looks good there. Okay, so today we have 3 satellites. We have the International Space Station, we have a weather satellite, and we have GPS. So I'm going to ask you guys to see if you can guess where you might be in orbit. What do you think? Does that look good? You comfortable there? Okay, so let's take a look at where they ended up. The International Space Station, I'm actually going to ask you to come in a little bit closer. You are the space station, you are the satellite that we have people living and working on, and so you're real close to the Earth. You're in low Earth orbit, which is about 200 to 400 miles away. So in our classroom, you're about ½ an inch away from the Earth, so stay real close here. The GPS satellite is in middle Earth orbit, and there's a constellation of satellites that helps us figure out where we are and puts our positions on a map. The weather satellite is in high Earth orbit, and that's about 22,000 miles away. It's in geosynchronous orbit, and so what it does is it orbits at the same rate that the Earth does. So it's always above the same spot on the Earth, and it gives us a good broad view of what we can see about the weather patterns. So nice job, guys.
Well, that gives us a really good view of where these satellites are in orbit around the Earth. I think we're going to see, in a minute, we're going to see a little animation here of what these satellites look like in orbit around the Earth. And right here, you're going to see on your screen, you're going to see the 3 orbits we're talking about today. One is called low Earth orbit. That place where the International Space Station was, 200 to 400 miles away. We have a medium Earth orbit, which again is around over 12,000 miles away from the Earth. And then last but not least, we have what's called geosynchronous orbit, which is out there over 22,000 miles away. And again, those are the 3 types of orbits that we're talking about today.
Okay, Dick, we just got an email in. It's a question from students at the Hathaway Brown School in Ohio. Hala, Alexa, and Abby want to know, can a satellite be pulled away from its orbit?
Great question, Alexa and Abby. A satellite can be pulled out of its orbit basically in 2 ways. One is by natural forces. We call the force of gravity is pulling down on these satellites, and basically the satellites are moving around in an orbit, as we've talked about, balancing the force of gravity, and sometimes atmospheric drag can cause satellites to slow up a little bit, and then gravity pulls them close to Earth, and we have to use thrusters to put the satellites back in the right orbit. But there's also sometimes scientists change where they want satellites to be to do their mission, and if they have to change where the satellite needs to be to do its mission effectively, then they also have to use thrusters or other ways to move that satellite out of its orbit. So there's several different ways satellites can be pulled out of their orbit, Matt.
Great answer to a great question. But have you ever wondered how the weathermen on TV are able to predict a forecast, even sometimes a week in advance? Well, weather satellites use different orbits to fulfill their mission and provide different images of the Earth. So before you go to the drawing board to design your satellite, let's learn a little bit more. Polar Operational Environmental Satellites, or POES, like those represented here by the blue balls, orbit at 450 to 470 miles above the Earth, and travel between the north and south poles, or what's called a polar orbit. The POES satellites provide full coverage of the planet twice a day. Geostationary Operational Environmental Satellites, or GOES, provide the weather images you see on the nightly news, as they track weather systems across the Western Hemisphere. GOES orbit the Earth at 22,500 miles above the equator, in geosynchronous orbit like the red balls here. Be it GOES or POES, they are operated by the National Oceanic and Atmospheric Administration, or NOAA. The Satellite Operations Control Center is staffed 24 hours a day, 7 days a week, to make sure that the satellites operate at full efficiency.
When you see any satellite imagery on TV, this is the actual instrument that data comes from. This is the imager, and it's on the Geostationary Operational Environmental Satellite, or GOES. This is 22,000 miles out in space, and it continuously stares at the Western Hemisphere. And I have here a model of the satellite, and this right here is the imager. The images produced by the imager are processed inside of the satellite and are incorporated in a data stream where they are transmitted down to the Earth through the antenna on board the satellite. For example, we have a direct broadcast capability where customers with their own antenna system can receive data directly from the satellite. We also have antennas that transmit back to us here, where we process the data on the ground and then distribute out to the National Weather Service and other customers.
It's a short trip from the NOAA Satellite Operation Facility to the World Weather Building in nearby Camp Springs, Maryland, where weather professionals work to carry out the mission of the National Weather Service.
The mission of the Weather Service is to save life and property from any kind of weather event, whether it be flooding, hurricanes, snowstorms, ocean storms, lightning, thunderstorms, tornadoes. That's our focus. We do that mission by understanding the atmosphere, observing the atmosphere, and predicting what the atmosphere is going to do.
Satellites play an important role in that process, as does the ability to read or interpret satellite imagery.
Here in the Gulf of Mexico, that's a line of thunderstorms. And there are some actually thunderstorms here popping over Mississippi. You can see thunderstorms here up Minnesota, trailing all the way back into South Dakota.
With the help of satellites, meteorologists can take a global view of the weather. The weather that will affect your weekend plans is somewhere else in the world right now, heading your way.
One of my favorite satellites in the space hangar is right over there, above the space shuttle. It's the Tracking Data and Relay Satellite, or TDRS. TDRS is a shining example of space communications. Notice those massive antennas. This first-generation TDRS satellite uses 5 types of antenna to relay information. And man, can this information move fast. A 20-volume encyclopedia per second to be exact. If there are 2,000 words per page, that equals about 250 million characters per second. The high-speed data transmission is vital to space communications on all NASA missions.
Houston, at this range, you're safe, so you have a go to cross under.
Okay. Astronauts rely on TDRS satellite as a lifeline back to Earth.
That's far enough to port. I need to go forward in the bay. Turn forward.
Astronomers receiving images from the Hubble telescope and scientists collecting an array of data about the Earth also use the unique capabilities of the TDRS. Perched 22,300 miles above the equator, a constellation of 7 TDRS satellites moves as the Earth moves in what is called a geosynchronous orbit. They appear to be fixed in space, hovering above the same spot on Earth. The next generation of TDRS satellites are currently being designed, tested, and manufactured. These satellites will include several new features. Innovative folding antennas meet NASA's requirements for reflectors with a large surface area. The steerable antennas can transmit and receive information from the fast-moving spacecraft. In development, each satellite goes through extensive testing to ensure a safe launch. Thousands of scientists and engineers have played a part in furthering the satellite design by presenting concepts to fulfill the TDRS mission. I think you can see why this is my favorite satellite in the space hangar. The Space Communications Network relies on this amazing piece of machinery. Now let's get back to the classroom. Your teachers have a pretty cool demonstration in store for you.
Thanks, Doug. We're setting up the next demonstration now. And in case you're just joining us, this is the Aerospace Academy. And we're coming to you from the Smithsonian National Air and Space Museum Stephen F. Udvar-Hazy Center. All right, Aaron, what's up next?
Well, as you just saw with the TDRS satellites, one of the main components of satellites are the communication systems. So we have Arjun here in the United States who's going to go visit his friend Ray over in China. But before he goes, he'd like to find out about the weather and things that are going on. So he needs to send a message. But since she's on the other side of the Earth, he can't just throw it right through. So Arjun's going to send it to one of these satellites up here in space. And this satellite's going to pass it on to the next, as this constellation of satellites is going to help him deliver his message. Oops. Good save, satellite. Okay, and so they pass the message back to Ray in China, and she can communicate. So we're going to trace that data stream that we just saw with this rope. So you can see that it started at the ground station in the United States, and it was passed to each of the satellites. Arjun uplinked the data stream to the first satellite, and they're passing it from one to the next, and then it's downlinked to the ground station in China. And if you guys will give it a little bit of shake, you can see how the data is transmitted. All of this travels at the speed of light, so it only takes less than a second for this all to happen. Nice job, guys. Looks good.
And in fact, our Aerospace Academy students across the nation are benefiting right now from an uplink and a downlink. This TV show is part of a data stream signal that is sent from the Udvar-Hazy Center to a satellite, then from the satellite to cable stations nationwide. Okay, we've received another email from a few students receiving this uplink. Kathy, Lauren, and Katie, they want to know, how fast does the rocket have to go to carry a satellite into orbit, Dick?
Well, Carly, Lauren, and Katie, that's a great question. The speed of a rocket putting a satellite in orbit is really dependent upon where that satellite's going to be put in orbit. And so for an example, I guess, if I take a low Earth orbit satellite, something like the space shuttle going into orbit or the International Space Station that we talked about before, you would have to get that satellite up there and get it going at about 17,500 miles an hour. That's about 5 miles a second in order for it to stay in orbit effectively and not be pulled back by gravity toward the Earth. So you got to be going pretty fast to get that satellite up there, Matt.
Wow, so to achieve orbit and transmit a signal, satellites need a fast ride to get into space. If you think about it, rockets are just like cannons.
As you know, a cannonball is a round object shot from cannons. Using an explosive base propellant, this artillery can launch a projectile over great distances. By examining these basic elements, Sir Isaac Newton, a 17th century scientist and mathematician, developed the Cannonball Theory to explain the laws of gravity. Modern scientists and engineers still use Newton's law to explain and predict the motion of satellites in orbit.
Let's imagine that Earth is a perfect sphere, so it's perfectly round, and let's imagine that there's no air, and let's imagine that there's only one tall mountain on Earth, and we put a cannon at the top of that mountain. So you fire the cannon, the cannonball goes out and it drops down and hits the Earth. And if you put a little more gunpowder in the cannon and you fire it, the cannonball comes out faster, it goes further and it still drops to Earth. But if you look at the curve of the motion of the cannonball, it's a bigger radius, it's a slower curve. And so Newton postulated that if you could fire the cannonball fast enough, the cannonball would drop towards the Earth at the same rate that the Earth is curving around, and therefore the cannonball could go all the way around the Earth and come back up the other side and hit the cannon from the other side.
So, what goes up doesn't always come down. In the last 54 years, there have been over 4,500 missions into space. Whenever we leave something in orbit that we are no longer using, it becomes space debris.
Space debris is any object in space, man-made or put into orbit by humans, that is not a functioning satellite.
Over the years, the amount of space debris has grown dramatically. In this animation, the red dots represent space debris, some of which are inactive or dead satellites. The green dots represent active satellites.
Currently, we have over 19,000 pieces of space debris in orbit, about 1,000 active satellites, and that's only the things that are big enough for us to see or to track with our radars in orbit. There might be hundreds of thousands of pieces that are, say, marble-sized that we can't track, and each one of those could destroy a satellite. A marble hitting a satellite can destroy it.
Damage to spacecraft from debris is an ongoing issue. The United States Air Force Space Surveillance System uses high-frequency radars and advanced telescopes to track space debris. To avoid a collision in space, scientists and engineers use the data they collect to protect satellites and spacecraft.
We use Newton's laws to figure out where satellites are now, where they're going to be in the future, where they were in the past. So I use Newton's laws every day in my job.
Did you know there are people living and working in space? The International Space Station is a habitable artificial satellite. As of this broadcast, 143 launches from Earth have delivered 233 individuals to work on this orbiting laboratory. Scientists conduct an array of experiments as it circles the Earth every 90 minutes. It's traveled more than 1.5 billion miles, which is more than 58,000 trips around the Earth. On board, 52 computers control the station, connected by 8 miles of electrical wire. The entire space station weighs almost 1 million pounds. Whew! Have you got all that? Section by section, the space station was assembled in space, making it the largest space construction project ever. As an international project, components have been built and launched by different countries. Space shuttles, or other types of spacecraft, dock very carefully, bringing astronauts, scientific equipment, and the additional parts for expansion. This massive orbiting laboratory's mission is to further scientific research and act as a base for space exploration. The International Space Station is one of man's most amazing achievements.
Okay, now that you're an expert in space science, it's time to design your satellite. Our teachers are handing out an activity sheet, and remember, you can find the same sheet online or you can use your own materials. Some of our students will be building models, but you can feel free to improvise using pipe cleaners, foam, and cardboard. Okay, we've got another email. This one's from Caroline and Anya at the Hathaway Brown School in Ohio, and they want to know what materials are used to make satellites.
That's another really great question. As you've seen from most of the satellites we've looked at today, they have solar panels, and those solar panels are made up of cells that help collect the sun's energy. All satellites also have a thin foil thermal blanket that helps protect them from the space's extreme temperature differences. And you saw on the TDRS's satellite that there's gold-clad wire mesh antennas that help it communicate. So a lot goes into it.
Now, millions and millions of dollars will be spent to build your satellite, so you need to make sure the design is stable. Well, let's take a look at a blueprint.
Satellite requirements. Your challenge is to design the next generation satellite for NASA. Determine your mission. What do you want to do in space? Pick a scientific instrument that will complete this mission. A telescope to look at Earth or distant planets. A camera to spy on foreign countries. A radar to track thunderstorms, or even a thermometer to measure temperatures. A satellite without a command computer serves no purpose. Include one in your design to gather data and control the onboard systems. Thrusters and a rocket motor are needed to maintain orbit and keep your satellite pointing towards the desired location so the antennas can successfully transmit and receive information. A satellite that does not communicate with Earth is a dead satellite. To power the systems, install solar panels. Sunlight converted into electricity is stored in batteries for continuous energy when the orbit moves the satellite into the Earth's shadow and is hidden from the sun. Cover your satellite with a thermal blanket to control the temperature of the electronics and keep them working properly. In space, the extreme temperatures could fry or freeze the scientific instruments. Remember, NASA is relying on you to complete this challenge. Failure to include these requirements will jeopardize the mission.
You've got a really great satellite going on here. Do you want to tell us what it does?
What it does is it takes messages from faraway places and sends them back to where they're supposed to go.
Very good. Very good. Are these the solar panels?
Mm-hmm.
Very nice. Good job. Okay. What are you doing? What does your satellite do?
My satellite is going to take pictures of space.
Okay. Good. Good. So it's an exploration satellite?
Yes.
Excellent. What are you drawing there?
I'm drawing solar panels.
Okay. Very good. Thank you.
Okay, wow, we got a lot of stuff being created here at this table. I wanted to ask Ariana what she's making here on her satellite.
Well, my satellite finds out more about space, and my three stuff that are on it would be the temperature and a satellite and some camera.
Wow, okay, I can see it all in your sketch there. We got your camera and your satellite and your antennas and everything. That's doing great. What are these things right here?
These are
like solar panels?
Solar panels.
Oh, solar panels get energy. Oh, that's cool. Let me try another one. Let's see let me see what Brian's up to here. What?
Well, I'm right now I'm building a satellite that's like Hubble. It can look far into space. This is its camera, and it has a bunch of cameras like all over, so like it can take pictures.
Oh, cool. So that's going to be like a scientific satellite that looks out into space.
Yes.
Cool.
Over the years, thousands of satellites have launched into space. Keep working on your design. Who knows, your satellite could be next in orbit. When you've finished your assignment, send us your designs and we'll send you an Aerospace Academy Award certificate. Email us for more information, and I can't wait to see your finished designs. Thanks for joining us, and congratulations! You've passed this lab of the Aerospace Academy. For the Fairfax Network, I'm Matt Fetters.